So let us begin my last part of the previous problem, which I started in the session 1. We are to prove the triangle inequality now. The triangle inequality. I was proving theorem 6.2 of Friedberg of the chapter of inner product space. And the problem was problem number D. Now, to start with, we will first write the left hand side. The left hand side is norm of x plus y whole square. I'll start with that. And this is nothing but, as before, we can write it as x plus y and x plus y. Now we can apply the two linearity property first of all. So we can write it as x comma x plus y, inner product of these two, plus y comma x plus y, inner product of that two. And next, in the next line, we can write it as x comma x plus x comma y, and this can be written as y comma x plus y comma y. Okay, and you know by definition this is norm squared, and we can write it as inner product of x comma y, and this is inner product of y comma x. Oyan Pandey raised you, if you have raised your hand if you want to say something, right in the chat box. And this is norm of y squared and you know we can write it as norm x squared x comma y, and we can write it as x comma y bar, norm of y squared. Okay, now you see that this is xy bar is the complex conjugate. This is the complex conjugate of that. And we know that when we actually say, for example, if I consider this complex number a plus ib and the conjugate of that a minus ib, if I deal with complex number and if I add these two, what do I get? We get 2a. 2a is what? If z is my complex number, if z is my complex number, so we write 2a as twice real part of z, if you can recall. So by keeping this rule in mind, we can write it as norm x squared, and x, this is the this plus this conjugate, I mean this real part, this term inner product and its conjugate, when added together, it gives the twice the real part of inner product of xy, and this is norm y squared. Okay, and we know that this must be less than or equal to norm x squared plus 2 mod of inner product of xy plus norm y squared. Okay, so this is obvious. So if I consider the modulus of this inner product, then that modulus will be greater than the real part of the inner product of xy. So that's therefore the inequality symbol has come over here. Okay, and just now we have proved that from Cauchy-Schwarz inequality that mod of this is less than or equal to norm of x into norm of y. So we can again use another inequality symbol, and we can use it as 2 into norm x norm y plus norm y square, and this is equal to, now I'm writing the equality symbol, because this equality, whenever I'm writing equality and inequality, you have to keep in mind that I am doing it very carefully, because you see when I start with this result left hand side, this term is equal to that term, that term is equal to that term, this term is equal to this, equals to this, equals to this, equals to this, but this term, in this term there is a term like real part of mod inner product of xy which is less than mod of x, mod of inner product of x comma y, and therefore inequality symbol is has come into picture. Another inequality symbol is, this inequality symbol has not been carried forward over here. This is a different inequality symbol. This inequality symbol, if we name it as 1, this inequality symbol name it as 2. This inequality symbol came from this particular result. And now I'm writing equality because this term is equal to the square of, and this term looks like a plus b whole square. Okay, ultimately if I want to connect, if I want to connect this let us not write left hand side. Okay, ultimately if I want to connect this part, norm of x plus y squared with this, so first of all we will write norm of x plus y squared, and this connection between the term this and that, these two connections will be made, these two terms will be connected with each other by the inequality this, not by this equality. You have to keep this, you have to understand that particular thing. This mathematical intricacy you have to understand. Students often mistakes in this particular portion. Who is getting connected to whom by what? Who is getting connected to whom by what? This is a very important part while when solving inequalities. And if I take the square root, we get the triangle inequality is proved. So we have successfully proved the triangle inequality. Now I am going to show, one problem. I'm considering example 8 of page 335 of the book. This problem I'm going to do, and this is you can to you this, you may think that this is a problem, but to me the thing which I was doing is also a problem. Anyways, I have to show this to you. So I'll consider this to be an example. The example is, in F3 is the set orthogonal? Is the set orthogonal? Okay, this I am going to prove. I'm going to show you this example now. This is a very important example, and for this I need to give you the definition of orthogonality. Orthogonality in the inner product space. So definition, first of all, I'm going to write the definition. Let capital V be an inner product space let V be an inner product space. Vectors x and y in V are orthogonal, orthogonal or perpendicular if inner product of these two vectors is equal to 0. A subset S of V is orthogonal if any two distinct vectors in S are orthogonal. Okay, a vector x in V is a unit vector if norm of x is equal to 1, is unit vector if norm of x equal to 1. Finally, a subset S of V is orthonormal if S is orthogonal and consists entirely of unit vectors. Now, probably you are thinking probably you are, if you are not reading carefully, probably you are thinking that this in orthogonality and orthonormality, these things are actually have come from outer space. They are something which is very new to you. But if you carefully observe, these things are not new to you. You did it in coordinate geometry many a times. How? Because when we set this two-dimensional plane and we consider the unit vector like I cap and j cap, okay, and when we considered the three-dimensional case like k vector, so we consider this to be the unit vectors, and we know that mod of I is equal to 1, mod of j is equal to 1, mod of k is equal to 1. Okay, we knew this. Now, and we also know that I and I dot j is equal to 0 because I and j are perpendicular. J dot k is equal to 0 because they are perpendicular. K dot I equals to 0. They are perpendicular. Okay, so we can say that I, and if I is a vector, j and is a vector, I and j are orthogonal to each other. J and k are orthogonal to each other. K and I are orthogonal to each other. And if I consider a set, S where I am keeping only these orthogonal vectors, all these, if you choose any two vectors from there, these vectors are orthogonal, then this set will be termed as orthogonal. The set is orthogonal set. And not only this particular set S consists of orthogonal vectors. Okay, two pairs are orthogonal. Not only this, these vectors are also the unit vectors. All these vectors are also unit vectors. And therefore, it is a set of orthogonal vectors, or individual vectors are unit vectors. So here S is orthonormal. This is the simple example which I am giving you and which you are familiar with. Okay, now when mathematicians do problem, they do not try to confine themselves in the domain of this 2D space and 3D space. Say they want to uplift them to higher dimensional space. And you know what do you mean by dimension? Dimension is not an alien type of quantity. Dimension is the number of elements present in the basis. So what they try to define something which is general, and these all these things which I've studied in our previous courses, they become the special case of that. So in case of modulus or and these unit vectors, they have defined this as the general case, general definition. This result is true for any vectors of any dimension. So therefore norm x is actually the generalization of mod x. Orthogonal vectors like this are the generalization of the unit vectors. The norm x is equal to 1, those vectors whose norm is 1 is called the unit vectors. These are the generalization of our I, j and k. So actually the same thing we are learning, but from a different perspective. Now I'm going to show that I'm going to check whether this set is orthogonal or not. Now in the book they have written just one line that yeah, it can be easily shown that this is this that, but you have is a huge calculation is involved, and I'm going to show you that calculation. Remember that we can declare a set to be orthogonal if we choose any two elements from this, and we can show that these two elements are orthogonal. Then only we can say that this the set is orthogonal. Okay, so I'm going to apply that result over here. Solution: let capital S is my set. I'm naming the set as 1 1 0 1 minus 1 1 minus 1 1 2. This is my set. Okay, let us choose two vectors, x which is 1 1 0 and y which is 1 minus 1 1. Okay, and we know in the previous class I told you that in Fn inner product of two vectors x comma y is actually defined as summation I goes from 1 to n ai bi bar. I also proved this result where x is equal to a1 a2 dot 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 an and y is equal to b1 b2 dot 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 bn. Okay, if you can recall, then I'm going to apply this particular thing over here. So inner product of x comma y will be inner product of 1 1 0 and 1 minus 1 1, and by this rule I can write it as 1 into 1 bar plus 1 into minus 1 bar plus 0 into 1 bar. Now these all 1 minus 1 1, these are all real numbers. So 1 bar is actually 1, minus 1 bar is actually minus 1, and 1 bar is actually 1. So we are ultimately getting what? 1 minus 1 plus 0, that is 0. Second, let us select, let z is equal to minus 1. Okay, let us write it over here, not here. Let y equal to this and let z is equal to minus 1 1 and 2. Now if I take the inner product of y comma z, what do I get? Take 1 minus 1 1 and z is minus 1 1 2. Okay, and if I apply this rule, you will get 1 into minus 1 bar plus minus 1 into 1 bar plus 1 into 2 bar, and that becomes minus 1, this becomes minus 1, and this becomes 2, and which is 0. If I consider x comma z, then let us consider 1 1 0 and minus 1 1 2, and by the rule we get 1 into minus 1 bar 1 into 1 bar plus 0 into 2 bar, and therefore this is minus 1, this is plus 1, this is 0, and that is equal to 0. So we see that any two pair, sorry, not any two pairs, sorry, any pair chosen from S are orthogonal, and so S is orthogonal. Okay, now this job is done. Also in the last part, in the last class I told you that in Fn, if x is equal to a1 a2 dot 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 an, okay, if the vector is like this, norm of x is defined as norm of a1 a2 dot 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 an, and which is equal to summation I goes from 1 to n mod ai square to the power half. I mean square root. We are taking the square root over here. So I'm going to check whether these vectors are unit vectors or not. Okay, I'm going to check whether these vectors are unit vectors or not. So let x equal to 1 1 0 and If it is so, then norm of x is equal to mod 1 square plus mod 1 squared plus mod of 0 squared root. Why it is so? Because you see, if I expand it, what do I get? We get mod a1 squared mod a2 squared dot 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 mod an squared. Okay, now I think you can correlate the two items, and that is equal to 1 plus 1, which is equal to root 2. If we consider y to be 1 minus 1 1, then norm of y will be mod of 1 squared mod of minus 1 squared mod of 1 squared, which is 1 plus 1 plus 1, which is root 3. And number z, sorry, the vector z is minus 1, 1, 2, and so norm of z is equal to 1, 1, and this is how much? 4 root 6, which is not equal to 1, which is not equal to 1, which is not equal to 1. And therefore, none of the vectors in S are unit vectors. So S is orthogonal but not orthonormal. We often encounter these terms in quantum mechanics, and therefore in quantum computation and quantum information. Okay, QI and QC. These terms are often very much used. Okay, so we have proved that. Now in the book, if you take the book, you will find that we can normalize the vector. If the vectors are not unit vectors, we can normalize it. Normalizing a vector means that from a non-unit vectors, out of non-unit vectors, you try to make it unit vector. So how can I do so? What is the process? So the next comes normalizing a vector, a very important term, normalizing a vector. In quantum mechanics, you will find this. In quantum mechanics, you will find this term normalization of the vector many a times. Okay, in quantum mechanics, suppose this is a vector. In Dirac notation, this is called Dirac notation. When we write x cap, this in mathematics we write, in physics we write, but in quantum mechanics, it is in classical physics we write it like this. And in quantum, we use the Dirac notation, we write this vector. Now, if we consider two vectors x and y, normalization means this thing. We are normalizing the thing. Probably we encountered this is a quantum bit. This is called a quantum bit in general. I'm not going into the details of that. So when I'm dividing this term by root 2, I'm taking two vectors x and y. These vectors are not normalized vectors, but when I'm dividing them by root 2, then they are becoming normalized. So I'm going to talk about this thing and that thing which I'm studying right now. They are all actually same. They are not different. So what is normalization of vectors? So to normalize a vector x, we write x normalized will be equal to x by norm x. That is the formula. It is called normalization of the vectors. Okay. So suppose it since now I can write that since capital S 1 1 0 1 minus 1 1 minus 1 1 2 is not orthonormal as the vectors inside it are not unit vectors. The vectors inside it are not unit vectors. So we normalize the vectors as follows. So x normalized in this case, let us write it in this manner, x normalized, that will be the x vector by norm of x. What is the x vector? X vector is 1 1 0. What is the norm of x? Norm of x is root 2. Y normalized, that will be y by norm y. Okay, and we can write it as 1 minus 1 1 by root 3. And z normalized, z by norm z is equal to, the vector z is minus 1 1 2 by norm of z root 6. Therefore these vectors, the new vector, these are the normalized vectors. Now let us construct a new set S prime by S prime contains all the normalized vectors 1 1 0 by root 2, 1 minus 1 1 by root 3, minus 1 1 2 by root 6. Okay, if you take two elements from there, now they are orthogonal. If you take any two elements from this set, they are orthogonal as before. And if you consider the norm of these uh, elements, you will find norm of this vector is root 2. So root 2 and root 2 will cancel each other. Okay, so therefore the vector has become normal. These vectors, this vector 1 1 0 was not unit vector, but 1 1 0 by root 2 has become the unit vector. So this is a unit vector, this is a unit vector, this is a unit vector, and therefore S prime is orthonormal set. S prime is orthonormal set. So I hope you have understood. I hope that you have understood what I meant to say. Let me show you the slides once again. That orthogonality plays a very important. I mean, in quantum mechanics, it is often said that if the two vectors you are not orthogonal to each other, then you cannot distinguish them. Orthogonality plays a very important role in quantum mechanics. Okay, so the vectors, you just go through your quantum mechanics books once again, and you'll find that how much important this particular thing is. So we begin with our usual mathematics of vector algebra in our school days, and now these vectors have been generalized to different dimension, and we have all these usual terminologies that we learned. They are being learned with another terminology and the new terminology, general set of terminology. And not only this, the same calculations we will be doing in quantum mechanics also. So if you see this book by Sakurai, Quantum Mechanics by Sakurai, then you will find that this book is not very big, but this book is wonderful, and it is written in the with respect to the perspective of linear algebra. So you can connect quantum mechanics with linear algebra. It's a very beautiful book. You can read if you get time once. Okay. If you really want to know quantum mechanics, you start with Sakurai. Then other good books are also there, because I know, I've come to know that you have so much pain in quantum mechanics. So that's why I'm saying, because in CSE, why I'm bothered in CSE, in 7th semester, there is a elective paper which is called quantum computing. And if you can take this paper, then I can help you, because this is my research topic. I have done PhD on quantum information theory. And if you are not interested in that, forget about quantum mechanics and everything. But linear algebra will be required as usual, always, in deep learning and neural network, everywhere. I don't know whether I'll be able to finish this problem or not, because time is running out. Let us try. A problem is there in the book, in the exercise. They have said that prove the parallelogram law on an inner product. The law is given by inner product space V is given by, that is, show that norm of x plus y squared plus norm of x minus y squared 2 into norm x squared 2 into norm y squared for all x comma y in V. Okay, so let us begin this proof. Time is also running out, so I'm just moving a little bit faster. I hope that you will be able to understand. And this is my last session of today's class, because as usual, I have to go to college. So we can write it in this manner. And then we can apply the linearity property. So we can write it as and then we can write it as okay. So we have written all this, and then we can and this is this quantity, you see this quantity, minus one is in the second term, with the second term, so it comes out as -1 bar, but -1 bar is same as -1 because it's a real number, so there will be no trouble. And here also I can write it as y something, some mistakes I have done. Oh, sorry. Okay. Minus y, just a minute. X minus y minus y. This should be minus y. This should be minus y, because x minus y is there. So x y x y x minus y x minus y. Sorry. And therefore, this will be xx xy yx yy xx minus xy. This will also be minus yx, and this will be minus y, and in the, if you want to write another once again, then that will become plus, because another minus sign is there, it will come out as -1 bar, so it will make this minus plus, so we get y comma y. and xy and minus xy will cancel each other, yx and minus yx will cancel each other, and ultimately I'm writing over here, we'll be getting is equal to 2 into inner product of x comma x and 2 into inner product of y comma y, and that is nothing but 2 into norm x squared, and that is 2 into norm y squared. Okay, so this is proved. Now you see that this is in general true, but if we consider in place of vector space V, if we consider the R2, let V is equal to R2, what happens? The elements of R2 are defined by this. You already know this. Many a times I have said. Okay, now if I apply the result which I proved right now, norm of x plus y squared, norm of x minus y squared, so that will be norm of a1 comma a2 plus b1 comma b2 squared, and this will be a1 comma a2 minus b1 comma b2 squared. Okay, and that is nothing but a1 plus b1, a2 plus b2 norm squared, and that is a1 minus b1, a2 minus b2 norm squared. Okay, and in place of a1 plus b1, you can imagine this to be c1, this to be c2, you can imagine this to be c1 prime, this to be c2 prime. So actually we have got c1 comma c2 norm squared, and we have got c1 prime comma c2 prime norm squared. And what is this? Just like our previous, I have told you that this is nothing but under square root sign this, and this is nothing but under square root sign that, and we can write it as and it is nothing but this, it is whole squared, and we can get it as mod c1 square mod c2 squared plus mod of c1 prime squared mod of c2 prime squared, and now resubstitute the values. This is a1 plus b1 mod of a1 plus b1 squared, this is a2 plus b2 squared, this is a1 minus b1 mod squared, and this is a2 minus b2 squared, which is the well-known parallelogram law in two-dimensional space. Parallelogram law in 2D space. Everything you can general proof from these general cases. So here I'm going to end my today's session. Okay, in the next class, that is on Monday, we are again going to meet. Okay, with Gram-Schmidt orthogonalization, orthonormalization, sorry.